a weak acid problem. We have our balanced chemical equation, so we can start our ice table, and we write our equilibrium constant expression. Again, we're not concerned with the concentration of water as it's a pure liquid and does not appear in the equilibrium constant expression. Alright, so we have our ice table constructed and we plug in our equilibrium values, the initial plus the change, into our equilibrium constant expression. And we see in order to solve x, we're going to have to solve the quadratic equation unless we can make the simplifying approximation. So let's test. Alright, so we've multiplied 1000 times Ka, and we find that this product is greater than the initial concentration of our acid, which is 0.1 here. So our approximation is not okay. We're going to have to solve this using the quadratic equation. Okay, so we're on our way of solving for x. We've done a cross multiplication. So we have 3.6 times 10 to the minus 4 times the quantity here in the denominator is going to be equal to x squared. We multiplied this out, and now we need to rearrange the equation to be in the form of ax squared plus bx plus c equals 0. Alright, so we have our quadratic equation set up, and we simply solve for x. When we solve for x, we get two roots. Only one of them makes physical sense, and we see that our second root here is nonsense. It doesn't make physical sense because we know that the reaction has to occur in the forward direction because we don't have any products. Now that we solve for x, we go back and answer the question. The question is asking us to determine the percent dissociation of this solution. Alright, the percent dissociation is the amount that's dissociated over our initial amount. So it's going to be hydronium ion concentration that is generated as a result of the dissociation over the initial concentration of our acid. So we're trying to calculate the percent that dissociates of this initial acid. So make sure you use the initial concentration of your acid, and it's multiplied by 100%. We see our final value is 5.8%. Remember, we said that the approximation was not okay, and this is consistent. The approximation tends not to be okay whenever the percent dissociation is greater than 5%. That leads to a greater than 5% error in your final value. Part B of this question is to calculate the percent dissociation of a more dilute solution of the same acid. We note here that we would expect that our percent dissociation in part B is going to be higher because as an acid becomes more dilute, we have a higher degree of dissociation. Okay, here we're set up for the second problem, part B. Our ice table is essentially the same, only we have a smaller concentration of the HA to start. So when we test our approximation, we're not going to be able to make the approximation, but I'm going to show you the math anyway. Alright, so we've multiplied Ka by 1000, and as expected, we see it is larger than our initial concentration of our acid, 0.01 molar, so our approximation is not okay. We're going to have to go through and solve this via the quadratic equation. As before, we need to put our equation in the form of ax squared plus bx plus c equals 0 in order to apply our quadratic equation solution. Alright, so we've applied our quadratic equation solution. We get two roots. There's only one of the two that makes physical sense. Again, the one here that's negative is nonsense because we know that some of this weak acid is going to react. So X1 here is our answer. It corresponds to the concentration of H3O+ and also the conjugate base. And finally, now that we have X, we can go back and answer our question, which is to determine the percent dissociation. All right, and we can calculate our percent dissociation, which comes out to be 45%. And as expected, our percent dissociation of our weak acid is higher for the more dilute solution of the weak acid.